So hello everyone. So good afternoon to all. So let us continue our the final lecture of my uh, talk. And so let me just recall that in the previous lecture we were trying to understand the notion of algebraic numbers as well as algebraic integers. And what we saw that if you take any algebraic number, so that will be always a root of an integer polynomial. Yeah, and that integer polynomial may not be monic, but we do get a polynomial with integer coefficients for which alpha is a root. Yeah, that is just because if we clear the denominators, then we see that by multiplying certain integer times a polynomial having the same root as the polynomial f as the root. Yeah, and then of course we can again take the GCD out and we can make that integer polynomial to be a primitive polynomial. Yeah, and what we defined that algebraic integer, for algebraic integers we impose the condition that the leading coefficient should be one of that integer polynomial. Yeah, and then we were trying to see this means actually in order to understand the algebraic numbers algebraically, what one would like to understand, collect all the polynomials for which alpha is a root, and then we were trying to see what will be collection of all such polynomials in terms of the natural map that we have from the polynomial ring Q of x to the set of complex number, which is the substitution map. And the kernel is precisely generated by a single element that we have seen because Q of x is a principal ideal domain. And then if we restrict the same, because alpha is a root of integer polynomial, we can very well restrict our map this from Q of x to Z of x. And then we will see that this is again a ring homomorphism. And in this case, the question is what will be the kernel, because here this ZX is not a principal ideal domain. But it turns out that proposition we have proven that the kernel will be precisely a principal ideal generated by the primitive irreducible polynomial for alpha. Yeah, and of course that is the result that we have proven, and so therefore this kernel will be a principal ideal. Yeah, now so today what we would like to discuss a proposition related to this, and which actually gives a criterion that when an algebraic number will be an algebraic integer. Yeah, so let me just write down it as a proposition and then we will proceed further. So the proposition is, so let us start with an algebraic number. So an algebraic number, so let me just write down an algebraic number alpha is an algebraic integer, if and only if, so here is the criterion that if and only if the primitive irreducible polynomial here that we were looking, the generator for the kernel actually should be, if we try to see, this was the primitive, this is generated by the primitive irreducible polynomial, but here is the condition that this will be algebraic integer if and only if the primitive irreducible, so primitive irreducible polynomial for alpha is monic. Yeah, so this is exactly it may look like very trivial, and it is in fact trivial that when so of course algebraic numbers are always a root of an integer polynomial, one can say primitive integer polynomial, and here what we are trying to say that it is an algebraic integer if and only if this is monic. Yeah, and the proof is, I hope you can give me the details. So let me just ask from you that how to proceed. Suppose, so let us first try to prove this direct part. That means suppose alpha is an algebraic integer. Yeah, then we need to prove that it is a root of a primitive irreducible polynomial which is monic. Yeah, how to proceed? Yeah, So it is so one thing is clear that from the above from the previous proposition that we have proven in the previous lecture, from the previous proposition, what we can say, that if you try to look, that kernel is actually generated by the primitive irreducible polynomial. So what we can say, that alpha is a root of a primitive irreducible polynomial. Alpha is a root of, say, primitive irreducible polynomial f of x belonging to this in this polynomial ring with integer coefficients. Yeah. Now our aim is to prove that this leading coefficient of this f of x is monic. Yeah. Then how to prove it? Can you proceed now? That how to prove that the leading coefficient for this polynomial has to be monic. So the hint is like that. Suppose the leading coefficient is not monic. Yeah. Suppose you can suppose that this polynomial f of x is not monic. Then what we can do? Then can any one of you say what will be the problem then? Yeah. If it is not monic, and we know that if you try to understand what are the zero, say what are the polynomials for which alpha is a root, is precisely generated by this f of x. Yeah. So therefore, what we can say, that then for any polynomial, if you take g of x, for which alpha is a root, yeah, then what will be for which alpha is a root, then what will be g of x? G of x will be multiple of this polynomial f of x, right? So g of x will be multiple of the polynomial f of x times, say, some other polynomial mx. Yeah. Where mx is another polynomial with integer coefficient. Yeah. So now what we see, that the leading coefficient of g of x will also be not monic. Yeah. Because leading coefficient of fx is not monic. And so if you multiply any other polynomial with fx, so the leading coefficient cannot be monic. Yeah. So what we see, that this implies that the leading that gx is not monic. Yeah. That gx cannot be monic. And gx cannot be monic, that means this alpha cannot be a root of any monic integer polynomial. Yeah. This implies there does not exist any polynomial, say any polynomial, any, let's say, monic polynomial. There does not exist any monic polynomial px belongs to z of x for which alpha is a root. Yeah. But this contradicts the fact that alpha is an algebraic integer. Yeah. Because we have assumed that this is an algebraic integer. Yeah. So but this contradicts, but this is a contradiction. Yeah. So that is the thing. And so therefore, if alpha is an algebraic integer, so it is a root of a primitive irreducible polynomial which is monic. Yeah. And conversely also, converse is obvious. Yeah. Conversely, because if you have a primitive irreducible integer polynomial which is monic, of course, by the very definition, this is an algebraic integer. Yeah. So the converse is obvious. And so therefore, what does this actually gives a criterion, that when one can say that an algebraic number will be an algebraic integer, provided one will be able to find the primitive irreducible polynomial for alpha. Yeah. And so this is exactly this proposition says. And so let us try to see, for example, So let us try to see that if you take, for example, if you take, let's say alpha is equal to, if you try to take 1 by 2 times 1 plus square root of 2, and in order to check whether it is an algebraic integer or not, what we would like to see, one need to know the one need to find a primitive irreducible polynomial for alpha. And if one tries to see that f of x will be of the form of 4x squared, then minus 4x, and then you have 1. So this is a primitive irreducible polynomial with integer coefficients, because the GCD of the coefficients is 1. So this is primitive. But this cannot be an algebraic integer because the leading coefficient is not 1. Yeah, here. Thus we see that, thus by the above proposition, what we can say, alpha is not an algebraic integer. Yeah, alpha is not an algebraic integer, and so therefore this actually gives an criterion how one can conclude that when an algebraic number is an algebraic integer. Okay, so as a corollary of the above proposition, and it is very trivial to verify that if you have a, for example, if you take a rational number which is an algebraic integer, then can you say what will be that rational number? Yeah, and this corollary says that will be precisely the integer. A rational number alpha is an algebraic integer if and only if, so this is if and only if alpha is an integer. And this you verify by yourself, and it is very trivial. As an application of the above proposition, you can prove that the rational numbers which are algebraic integers are precisely integers. And so in a sense, one can try to think that these algebraic integers are a generalization of this set of integers in a sense. Yeah. But however, let me just say that the concept, like the definition of algebraic integers, actually has important, actually it is important in number theory. And the definition, if you try to look, is actually it is not very easy to convince that why the definition of algebraic integer is of this form, that the leading coefficient should be 1. Yeah. However, so let us try to give a rough idea that what is going on with this definition, and what actually this the definition of algebraic integers actually do. Yeah, so what we would like to say that this leading coefficients in the definition of algebraic integer can be thought of as a denominator. So roughly, so this I am telling as roughly that leading coefficients. So let me just write down that leading coefficient of an algebraic integer, leading coefficient for, so let me write down the leading coefficient for f of x can be thought of as a denominator, and where alpha is an algebraic integer. If alpha is an algebraic integer, so roughly what does this leading coefficient being 1, that means that there is no denominator for this algebraic integer. But it is not completely true. This is not precisely true. We will see certain examples, but philosophically or conceptually, it do actually the same thing. And here is the reason that's why I am telling like this. So for example, if you have if alpha is for example, if alpha is an algebraic number, say if alpha is an algebraic number, that means what? That alpha is a root of an integer polynomial. Let's say f of x will be, let's say, something like d times x to the power n. plus an minus 1, say x to the power n minus 1 plus, and so on and so forth, a naught. Yeah. So alpha is an algebraic number. That means alpha is a root of some integer polynomial. So this belongs to z of x. Now what I would like to say that this algebraic number contains certain denominator, and if you clear that denominator, then this alpha will be an algebraic integer. So what do I mean to say? That and this belongs such that f of alpha is 0, then d alpha is in fact an algebraic integer. Then d alpha is an algebraic integer. And this is just because this d alpha will be a root of a monic integer polynomial. Because, so let me just write down, because if you take the polynomial g of x to be equal to, let's say, x to the power n, which should be monic, so we have taken the leading coefficient to be 1, and then look an minus 1 x to the power n minus 1, and then plus d times an minus 2 x to the power n minus 2, and so on so forth, plus d to the power, let's say, n minus 2, and then a1x plus d to the power n minus 1 a naught. Yeah. And now if you put g of alpha, then what we see that we can take d to the power n minus 1 as a common, so d to the power n minus 1 times f of alpha. Because, sorry, g of d alpha I should take here as g of d alpha, because our claim is that d alpha is an algebraic integer. Yeah. So here it should be g of d alpha. So g of d alpha is precisely this, which is equal to 0. And so therefore what we see that actually this leading coefficients, if you multiply with any algebraic numbers for which this is root of a polynomial, then that d alpha will be an algebraic integer. So in this sense, one can always think of the leading coefficients as a denominator for algebraic integers. Yeah. And so however, that as I told, that this is not precisely the denominator, but most often it do the job. And so this is not the precise denominator. For this, let me just give you an example. So for example, if we try to see, for example, if you take alpha to be, let's say, 1 by 2 times 1 plus square root of 2, and well, so what we see that this is not an algebraic integer that we have just now told this example here. This is not an algebraic integer here, but what actually we can prove that, but then 2 alpha is an algebraic integer, then 2 alpha is an algebraic integer. Yeah. But if you try to look the leading coefficient of this polynomial for alpha, this leading coefficient is 4. Yeah. But in fact, if you in fact 2 does the job here, because one can prove that 2 alpha is an algebraic integer. Yeah. So actually, so there, however, the leading coefficient is 4. So therefore this denominator word actually is not precise, but it is most often actually it is like that. Yeah. So this is the one thing. And also, as you can see from this example, that one may not quickly jump to the fact that if a certain number contains certain denominator like this, then one should not quickly say that that number cannot be algebraic integer, because we have another example where this actually is this intuition actually will give you the wrong answer. Because if you take this cube root of unity, say 1 by 2 times minus 1 plus square root of minus 3. So this is an algebraic integer, because zeta is a root of, since zeta is a root of, the integer polynomial. Let's say, for example, x square plus x plus 1, yeah, which is a primitive. Oh, sorry, which is monic. Yeah. But here we have the denominator half, and so that's what I would like to convince, that just by looking the denominators, one should not make any impression that that is not an algebraic integer. Yeah. So therefore, these two examples actually give that this, as we have seen, that denominator, it can be thought of as a denominator, but this is not precisely the thing that actually this is being told here. Yeah, but roughly or vaguely, the leading coefficient actually do the similar job. Yeah. Okay, so this is the thing that algebraic integers that we have discussed now actually has uh, certain tricky things which one need to remember. And so now let me, our aim is to discuss certain algebra related to this thing. And so for example, as we have seen, that if you try to take how to find the algebraic integers, or how they look like, and what are the properties of these algebraic integers. So for this, let me start with, if you know a bit of field theory, then it's fine. Otherwise, you can assume for the time being. And from now onwards, I am going to give many of the facts without proof. And actually, it covers what actually these algebraic integers have important properties and the related things. Yeah. So if one tries to take this this prime field, prime infinite field set of rational numbers, and this if you try to look a bigger field which contains q, but it is a finite extension of q. So let me, q sits inside, say, a finite extension k of q, and such k is known as number field k over q. If you one tries to measure the dimension of this k as a vector space over q, and if it is finite, then such a k is known as number field. Yeah, number field. And so if you have k over q is a number field whose dimension or degree of k over q is n, so degree are, so this is known as degree of k over q, degree of the field k over q. So it is an extension field of the field of rational numbers. So degree here is n. Then what one does, that one looks the certain collection. So this collection that we are going to look at all those numbers from k such that alpha is an algebraic integer. Yeah, algebraic integer. By the way, let me just say that every element of k is an algebraic number. So so it is, again, by one can prove that if you have finite extension of q, then every element of k is an algebraic number. So for every alpha belongs to k, alpha is an algebraic number. Yeah. So here what we are collect all those elements which are actually algebraic integers, and let us denote it by the notation as OK. And one can very well check that if you try to, by the above corollary that we have taken, that if you take any rational number which is an algebraic integer, has to be an integer. And so therefore what we see, that so set of integers z sits inside this set, and in fact it can be proved that this OK is an integral domain. Yeah, that means addition and multiplication of algebraic integers in OK is again an algebraic integer. Yeah, is an integral domain. And so if you don't know what do we mean by this extension field and finite extension of q, one can very well look the very simple non-trivial extensions like k. One can very well take to be this quadratic field q is square root d, where d is a square free integer. D is square free integer. Yeah. And then if one tries to see what will be the OK, then in this case, OK will look like this will be of two form. So one of them will have a very simple expression in terms of, let's say, in terms of this thing, what I would like to say, that z square root of d, and the other one has a similar expression. So let me just write it down. So this one, so this set of algebraic integer will look like z square root of d, and this is case when d is 2 or 3 mod 4. And if d is 1 mod 4, it has a bit different type of representation, but of course related with d. So this will be of the form 1 by 2 times 1 plus square root of d. And in fact, so therefore in the case of quadratic fields, and this is a degree 2 extension of the set of rationals, and if one tries to look the algebraic integers, they will be of this form. And so therefore whatever I am going to speak, if one is not comfortable with this general notation, okay, one can very well think of okay as z square root of d, or z 1 plus square root of d by 2. So this will actually correspond to your quadratic extension over Q, but these results that we are going to say is in fact true for any finite extension of this rational field. Yeah. Okay, so let me just say that so what is going on, that K over Q has degree n. So it has degree n, and the corresponding thing that if one tries to look the corresponding generalization of integers to algebraic integers, so here we have this, and this also has extension in a sense that this also has extension n. And here, so here it this extension, this n is written as a dimension of K over Q as a vector space, but here n can also be thought of as that okay is a z module, that, and the notion of module you are going to see in the next week lectures. So this n can be thought of here as the rank of the module okay as a z module. So you will see in the module theory that there is a notion of rank of a module, for example, over a principal ideal domain in this case. And there the rank is well defined, and the notion of rank is very much similar to the dimension of a vector space over a field. But of course, it is a generalization of this dimension of vector space over a field for rings. So instead of fields, one can take rings, and one can study the similar properties that the vector space has, and this is known as a module. And so therefore those algebraic integers also has an extension as okay, and this is rank n extension from z. And so what I would like to say that, so and here okay, if you are not comfortable, you can think of this, and in this case your this rank will be equal to 2. Yeah.
Balesh,
Yes.
can you just request that they just say free module also? Means they will read the definition later.
Yes, yeah, actually it will be a free module of rank n. Yeah, so yeah, so this these things you will be studying maybe in the next week, but it turns out that this okay is a free module of rank n, and the definition of free module of finite rank is very much similar to the notion of like linear independence that you know in the case of vector spaces. Yeah, so they will be very much similar to that. And so what I would like to just so far, any question apart from these things, that if you have any doubts or anything, so let me just pause for some seconds and then we will continue.
No, sir.
Okay, fine. So let me just say that the property that this OK has, as we know that this set of ring of integers has a very nice property. Of course, it is a Euclidean domain, so it has a very nice properties. But if you take like the extensions of Z as a module like OK, so they may not have a nice properties like Z. In fact, we have seen that Z is square root of D. Oh, sorry, Z is square root of -5 even is not a UFD. Yeah. Yeah. So we have seen these things. So therefore, this OK may not have nice properties, but as element wise. But what I would like to say that in fact OK enjoy the very nice property at the ideal level, and that is known as OK is a Dedekind domain. Dedekind domain. And so let me, since we are discussing in this whole lecture the notion of factorization, so let me quickly say what do we mean by Dedekind domain in terms of factorization. So that is what is the meaning of this is that every non-zero ideal of OK can be uniquely written as product of prime ideals, written as product of prime ideals. Yeah. And so here uniqueness is up to the ordering of the term. So if you change the ordering, so that is allowed, but up to that ordering. So every ideal has a factorization in terms of prime ideals, but so OK may not have the unique factorization element wise. So as we have seen here that z square root of -5 do not have that unique factorization. And here also one cannot say, but if one tries to see that factorization in terms of ideals that we have at some point told while defining the uniqueness of factorizations, and ambiguities lying there because of units and associates. And if you ignore that units and associates, and if you talk of in terms of ideals, so OK has such a nice property. And in fact, the definition of Dedekind domain can be taken to be as this thing that we say an integral domain to be a Dedekind domain in which every non-zero ideal can be uniquely written as a product of prime ideals. Yeah. And since we are talking of the notion of product of prime ideals, so what do we mean by product of ideals? So let me just define what do we mean by the product of ideals. So this is the definition. And so for example, if you have two ideals, say let A and B be two ideals of OK. In fact, this product of ideals can be defined for general ring R. One can define it for general ring R, but in order to not deviate much, so we will be only focusing on this ring of algebraic integers, but this notion can be defined for any general ring or product of ideals. Yeah. Now, can anyone of say how one can define this the definition for the product of two ideals? So our aim is to out of these two ideals, I need to define a certain product which is again an ideal. Yeah. So that is our actually aim, that we would like to define a product which is actually again an ideal. So can you have a natural, so for example, if we define for example AB to be collection of all those elements alpha beta such that alpha belongs to A and beta belongs to say B, where A and B are ideals of OK, then does AB is an ideal? Yeah. So does,
we can take finite sum of these.
yeah, we can take,
right?
but what about AB? So it will be an ideal or not? Is it an ideal or no?
No, sir.
Why?
Need not be an additive group.
Yes, yeah. For example, if you take alpha beta plus gamma delta, then how will you show that where alpha beta and gamma delta belongs to AB, then how to show that alpha beta plus gamma delta is also in AB? Yeah. So therefore, this property, as you can see, may not hold inside this because this is only just the products of the elements of A and elements of B. But for the definition of ideal, at least it should have additive. It should be an additive group. Yeah. So therefore, what we can do that, well, it is not an ideal, but we can take this set as a generating set for this product of ideals. Yeah. And so what one can define that, well, one can say that, so one can say that look at the set generated, look at the ideal generated by this set. Yeah. And then now this is an ideal. Yeah. And once we say that ideal generated by this set, that means look at all finite sums of elements of this sort. Yeah, so the typical element of now AB will look like summation over a finite sum alpha I beta I. Yeah, belongs to this. And by the very definition, it is an ideal because we are generating an ideal out of this set. Yeah. And so since we are generating, so therefore, by the very definition of the generating, we can say that it is the smallest ideal which contains such products. Yeah. So that is the exactly thing that it can be checked that this AB is this ideal. We can check that this ideal AB. So let me just write down that ideal AB is the smallest ideal for which smallest ideal which contains the elements, which contains all products A alpha times beta, where alpha belongs to A and beta belongs to the ideal B. Yeah, so this is the definition of the product of ideal, and it was then idea of Dedekind to actually extend the notion of divisibility to ideals in analogy with the notion of divisibility as an element. Yeah, and this is the idea of Dedekind to define the notion of what is so-called this divisibility at the level of ideals. Yeah, so let me just make that definition. And what it says that if you have an ideal, say, so let's say an ideal, let's say A of OK, and in fact this divisibility, as I told, that this product of ideal can be defined for general ring, and this divisibility in fact also can be defined for general ring. But here we will be focusing only for this ring of algebraic integer. Yeah. So this divides. So let's say divides another ideal, B of OK, and the definition is very much similar to the case as an element. If there exists an ideal C of OK, and here when we say general ring, wherever I'm writing OK, one need to replace it by general ring. Yeah, so such that this B can be written as A times C. So therefore, this is the meaning of divisibility of ideal, that one ideal divides the other if we are able to find another ideal C for which this condition holds. Yeah, and so this is the notion of the divisibility of an ideals. And let us try to just see quickly how the notion of these multiplication of ideals actually do the job or can be used in, for example, in the ring of integers. And here what we know that z square root, for example, -5 is not an UFD. Yeah, is not an, let's say, UFD. So what, and this is just because we have 6 as an element can be written as two ways of different in terms of irreducible elements, say 1 plus square root of -5 and then 1 minus square root of -5. But what I would like to say that, well, this representation is not unique as an element, but if one tries to look as element 6 as an ideal, so that means ideal generated by 6 inside this thing. So 6 ideal generated by this will be 6 times z square root of -5. And if you write 6 as an ideal, then there is a possibility, or in fact one can write the ideal 6 as a product of prime ideals uniquely. And actually that product actually takes care of a common representative for this. If you think of ideal 2, ideal generated by 2 and ideal generated by 3, and another product you have ideal generated by say 1 plus square root of minus 5. I will write it as in sort delta. So 1 plus delta and 1 minus delta. So when we write in terms of ideals, so there is a possibility to find suitable ideals which actually commonly true for all these things, all these representative as an ideal. And so there actually so we can have so there actually this different way of writing as an element will actually be not in the picture, and that's one can do. And so the very naive intuition that one applies that, well, if I would like to write this principal ideal as a common as a product of ideals which actually takes care of this 2 as well as 1 this 1 plus square root of minus 5, then one need to find an element rho inside if I give it as a name R, a ring R, a rho in R, such that rho divides 2 and rho divides say 1 plus delta. Yeah, we need to find a common element. And in terms of ideal, if one tries to write, that means divide is to contain, means 2 should lie in the principal ideal generated by rho, and 1 plus delta should also lie in the principal ideal generated by rho. Yeah, but it turns out that there is no such a single element which actually does this job. Yeah, so it turns out there does not exist any such row. Yeah, but what one can do is that we would like to find an ideal which actually in which 2 as well as this element both lies. So well, we can do that thing even such element doesn't exist, but we can find such ideal, but only the difference will be that that ideal may not be principal ideal. And if one would like to find an ideal which contains a given 2 element, the natural way to look at the ideal generated by these 2 elements. Yeah, and of course these 2 elements will lie in that ideal. Yeah, this is by the very definition. And so let us try to look A to be the ideal generated by 2 and 1 plus delta. Yeah, so this contains 2 as well as 1 plus delta. And similarly, let us try to take B to be the ideal generated by 3 and let's say 1 plus delta. Yeah, and now what I would like to say that if you look the conjugate ideal, one can define the conjugate of an ideal in this ring just by looking the alpha bar, where alpha is an element of ideal. Then one can prove that conjugate is also an ideal. And in this case, it turns out that the conjugate ideal will be generated by 2 and 1 minus delta. And here B, conjugate ideal of B, is generated by 3 and 1 minus delta. And if one tries to compute A bar, for example, so A bar one can compute as, then what one can see that A bar will be generated by 4, 2 times 2, and then we have 2 times 1 plus delta. Yeah, which is 2 plus 2 delta. Let me just quickly write. So this will be 2 plus 2 delta. And then we have 2 minus 2 delta. And then we have the product 1 plus delta and 1 minus delta, which is equal to 6 that we know. Yeah, from here, that we know from here. Yeah. And so one can check that this product A bar can be generated by this. And in fact, this A bar, in fact, can be thought of, and in fact, it is equal to A bar is equal to the principal ideal generated by 2. It is just because that A bar is contained in A bar is contained in the principal ideal generated by 2, because the generators of A bar contains 2 as a factor. That is obvious. And conversely, 2 belongs to a bar, that's also very obvious because 6 and 4 lies inside a bar, so therefore their difference will also lie inside a bar, and so therefore ideal generated by 2 is contained in a bar, and hence we have this result. Yeah, and similar arguments one can also prove that this product AB can this product of ideal AB will be generated by 6 and 2 plus 2 delta, and just take the element wise multiplication for the generators, 3 plus 3 delta, and then you have minus 4 plus 2 delta, and this one will correspond to exactly the 1 plus delta and 1 plus delta. Yeah, and here also similarly one can prove that this ideal AB is precisely the ideal generated, principal ideal generated by the element 1 plus delta, and the similar argument that I gave here will work here for 1 plus delta. And also one can prove that if you take the conjugate of this will be generated by the 1 minus delta, and BB bar is the principal ideal generated by, let's say 3. Yeah, let's say 3. And so therefore if we try to write it down now in terms of principal ideal, what will be the principal, if we write the factorization of the principal ideal generated by 6, then one can in fact see that we can get a common generalization, or we can get a common factorization of 6 as well as 1 plus delta, and for this will be exactly the principal ideal generated by 2 and 3. And as we see that 2 principal ideal 2 is same as a bar, and principal ideal 3 is same as BB bar. Yeah, and as we know that 6 is also equal to one principal ideal generated by 1 plus delta and 1 minus delta, and this is equal to the ideal generated by AB, which is here, and ideal generated by this thing AB bar. Yeah, and so therefore what we see from here that this ideal generated by 6 has a common refinement, or common we get a common ideals which takes care of this factorization as well as this factorization, which is AA bar and BB bar. Yeah. And so at the level of ideals, we do get a product of prime ideals, which that any ideal can be written as a product of prime ideal, and that can be checked as that they have this factorization in terms of ideals. Yeah, so this is just an example that how this product of ideals can be used to make certain things common or unique in order to do the computations. Yeah. Okay, so let me now proceed further. And so what our aim is to just say that after defining this product of ideals, actually one would like to put certain structure on this collection of all ideals of OK. And so let me just write a notation that if we take this I, script I, to be the all non-zero ideals, all non-zero ideals of OK. Yeah, and one can define an operation on this set of ideals as, if one tries to look operation on this set, just look to ideals A and B and send it to the product of these ideals AB. Yeah, and then one can check that this operation is a binary operation, so is a binary operation. And so we have this binary operation, and also it can be checked that this operation is commutative as well as associative, and the identity element in this collection is precisely the ideal generated by 1, principal ideal generated by 1, which is the full ring OK itself, because A times OK is same as OK times A, which is equal to the ideal. Yeah, and so therefore what we see from here that this is actually a monad. So I is in fact a monad, Yeah, and so let me just say that so therefore, and since as we have told that is a Dedekind domain, that means every ideal can be written as a product of prime ideals. So for this monad, so these prime ideals are the generators for this monad. Yeah, so non-zero, so non-zero prime ideals of OK are generators for script I. Yeah, and so in particular what we know that set of the integer ring of integers is contained inside the ring of algebraic integers, and one is always interested to check whether the prime integers p lying here sits as a prime inside OK or not. And since it has a factorization in terms of ideal, so therefore the principal ideal generated by p inside OK, that can be denoted as POK, and this is the notation for me as principal ideal generated by P, can be written as a product of prime ideals. And when we say prime ideals means prime powers is included, because we are not telling that product of prime product of distinct prime ideals. Yeah, so therefore POK can be written as P1 to the power E1, and let's say PI, let's say PG to the power EG. Yeah, and EI are the powers of these prime ideals. Yeah, and so what I would like to just say that if so this is the factorization, and here EI is in the literature, EI is in the literature is known as the ramification degree of PI, and there is also certain numbers which are known as FI, and FI are actually is the cardinality of OK mod this PI. Actually, it turns out that this ring of integers OK, ring of algebraic integers OK, is a Dedekind domain, and so every non-zero prime ideal is maximal. So in this, that every non-zero prime ideal is maximal, it has this property also. Every non-zero prime ideal is maximal, and so therefore if you try to look the quotient OK mod P will be a field, and it turns out that will be a finite field, and so its cardinality is finite, and so if its cardinality is finite, this will be a finite field, and we know if you know a bit of finite field, then the cardinality of finite field will be some prime to the power, some prime power, and in this case this prime power will be exactly the same P that we have started with here, same P to the power Fi. Yeah, and so let me just write it properly. So OK mod this thing is precisely this, and Fi is known as the residual degree of Pi. Fi is known as a residual degree of this Pi. Yeah, and so if one would like to study a bit of algebraic number theory, then there is a remarkable relation between this G number of factors and this power and this residual degree and the extension of K over Q, this which is N here. So and the result what does it say is that actually I from 1 to Z, EI Fi is equal to N. So therefore, what it says that if you take a prime integer, so that will be an element inside this ring of algebraic integers. So it may happen that this, if you look at the ideal generated by this may not be a prime ideal in OK. So it will have certain factorization. And what does this relation says? Actually, simply that the number of prime factors cannot be more than n, more than the degree. Yeah. So therefore, thus we see from above that if you take a prime P inside integers which lies inside OK, and if you look at the prime ideal generated by P, so P cannot have more than n distinct prime factors in its factorization. Yeah, so this is the one thing that I would like to say. And now let me say a bit more, since what we know that this script I is a monad, and but usually in algebra one is always interested to have a better structures, and one would like to make it as a group. But we can check that the inverse of any ideal will not be here except the identity element, of course. And then one would like to attach more elements to this script I to make it in terms of a group. Yeah, and so let me just say that so in order to find the inverse, what one need to do, that for inverse what we need to find an element B such that A times B should be equal to the identity element, which is okay in this case.
So,
And
Balesh,
yes, sir.
in before going, maybe one example that the Jadai pay 235 explanation, maybe.
Yes, yeah, right. So like in the case of Zi, we have seen, right? So yeah, in the case of Zi, what we have seen that if you take R to be, for example, Zi, then what we have seen that this Z is inside here, and what we saw that what are all primes which will be the product of two primes. Yeah, and if you see, I think we have proven that if you take P congruent to 1 mod 4, yeah, like if you take, for example, 5, yeah, 5 is congruent to 1 mod 4, and then 5 can be written as say product of two elements, say pi bar, yeah, where this and here what you see that you can write, I think it as 2 plus I, yeah, and 2 minus I, yeah. And so therefore if one tries to look 5 as a principal ideal generated by in Zi, which I mean to say 5 times Zi, then this can be written as a product of two ideals, precisely 2 plus I, ideal generated by 2 plus I, and ideal generated by 2 minus I. And we have seen that this 2 plus I and 2 minus I are prime elements. So the ideal generated by them will be a prime ideal. And so this is the factorization, for example, of 5, which is a prime integer. But if you look inside Z, it will have exactly two factorization. But however, this result says that you cannot have more than n, and it may happen that a prime P, for example, have P OK is precisely equal to say P1, P2, and so on Pn. And in this case, it's known as, there is a terminology which says that this prime integer P belongs to Z, it splits completely in OK. It splits completely inside the ring of integers OK. Yeah, so this is the thing. So should I continue, or I think time is up, or can I take 5 minutes more?
Yeah, you can take actually better actually. One more thing is that this Jada 5 by 2 plus I also prime ideal, which you are saying. So that EIFI can be get from here. With that,
Yes,
it will
yeah.
be
Now since this relation EIFI has to be true, yeah, that means E1 F1 plus E2 F2 is equal to 2. Now since these are, as you can see that E1 is 1, yeah, so this will be 1, and E2 is also 1, right? And this has to be equal to 2, and one can actually check that if you try to look the field, this thing Zi mod 2 plus I, Zi mod 2 plus I ideal, that will be a finite field. And if you try to see what will be this finite field's cardinality, and then one can check that the cardinality of this finite field will be exactly equal to norm of this element. I think you have done this thing in tutorial, right? Yeah. So that will be exactly 5. So therefore the power is here is 1. So this will be 1 into 1 plus 1 into 1, which is 2. Yeah. And in fact here, as we can see, that EI, FI are same. Yeah. And this is just because this is a Galois extension. That is again a result that if you have a Galois extension, then all these EI will be same and FIs will be same. And in that case, you will have a very nice relation, just E times F times G is equal to M. Yeah. So anyway, so this is the thing. And just let me say maybe 5 minutes.
Yeah, please take.
Yeah, so one would like to make the include the inverses, and if you try to include the inverses, so what you need to have this relation. And if you try, what will be B will be A inverse, and one is interested what will be the A inverse. And if one tries to see this definition, that we need to include all the elements of our field K, for which if we multiply that element to A, should lie inside OK. Yeah, X OK should be contained, sorry, XA should be contained inside OK. XA should be contained inside OK. Yeah. And in fact, it can be checked that this is not an ideal. This is not an ideal. Yeah. And in fact, it turns out that this cannot be contained inside OK. So this will be outside of OK, and it is not an ideal, but it is essentially an ideal. And essentially what I mean to say that A inverse in fact is not an ideal, but it is a fractional ideal, is a fractional ideal. So that means there are certain fraction in this representation. If you clear that denominator to make that thing to lie inside OK, that is by the very definition of fractional ideal. So let me just give the definition that A is said to be a fractional ideal, and ideal. So A subset of K is said to be a fractional ideal. Fractional ideal of K, let's say of K, if this should be non-zero, non-zero subset of K, and if A is an OK module, if A is an OK submodule, that module theory you will study in next week, submodule for which there exists say denominator C belongs to K star, such that C times A is contained inside OK. So what it says that this set contains certain fraction, and if you clear that fraction C, and if you multiply with A, that will lie inside OK. And this is exactly the definition of fractional ideal. Yeah. So there will be certain fraction up to that fraction. This is an ideal. Let's try to say. And it is an OK submodule. It has to be by the very definition. And so therefore, if you include all those fractional ideals and make our set, extend our set I to include all those fractional ideals, and if you denote it by script F to be the all non-zero fractional ideals. By the way, by the very definition of fractional ideal, any ideal is a fractional ideal, that you can check. Any ideal is a fractional ideal. Just because one can take C to be 1, and it is any ideal is of course an OK submodule, that you will see by the very definition of module. Thing is satisfied, and therefore, and one can check that this is a group. This is an abelian group. Abelian group with respect to multiplication of ideals. Yeah, multiplication of ideals, and it has a natural subgroup lying inside this script F, which I will write as capital P, which is all non-zero principal fractional ideals. Principal fractional ideals. And if you try to look at the quotient, which is that will be again a group. So let's say F by P, and this is known as the Picard or class group of the number field K. Picard group, or in number theory it is very much known as the class group of K, number field K. And it turns out that for a number field, this Picard group or class group is a finite group. Yeah, and this cardinal order of this group is finite, and this is known as the class number of K, class number of K. And here is a theorem which actually this finiteness of this class number is also a non-trivial result in number theory. And what actually this class number does, that this OK is a PID, OK is a principal ideal domain if and only if this class number is 1. And actually, so the class number actually measures how far our ring of algebraic number is far from being a principal ideal domain. Yeah. So this is the thing just I would like to mention, and now I would like to stop. Thank you very much, and all the best for your career. And so
Yeah, thank you very much. And I'll just add one comment here.
Yes.
Okay is UFD if and only if it is PID. That is another beauty.
Yeah, that is another result in number theory, that UFD and PIDs in number field case are same. So only the problem lies to find either one can prove UFD or PID. Yes.
Okay, so any questions?